Okay, let's get a start on Unit 2, Part 2. So now we're looking more at differentiation, like we did before, but we're going to look at some basic rules. And we're going to start today with connecting differentiability and continuity. So yesterday or the other day, Thursday, we talked about what would happen or that sometimes a limit does not exist. And we just said, kind of trust me on that if there's a sharp turn or a cusp, the limit's not going to exist. Okay, so that's what I want to work on today. Oops. Okay, so let's go ahead and copy down these notes. So we've talked about local linearity before. And we said, what does it mean if a function is differentiable at a point? And we've talked about it, something being differentiable. That means it has a derivative. Well, now we're going to put that together with the local linearity. And we're going to say that it means that the graph is locally linear at that point. And if it's locally linear, the derivative will exist. And basically what that means is that the graph is smooth and continuous at that point. And when we zoom in on it, it looks like a line. Now, it seems like, well, wouldn't every graph look like a line if you zoomed in on it? Not necessarily. Okay, so we're going to look at two examples here. And I put these graphs in my calculator. Okay, so here they are. Okay, so I have the first one with absolute value is blue. The second one is red. Okay, so let me look at if I graph. There's the second graph. And let me see. Turn off that graph. And here is the first graph. Okay, so the blue one is the absolute value graph. The red one is this one right here. Okay, so let me turn on both at the same time. And notice when I graph them, they look almost identical. Okay, so I'm going to look at the corner right there because we said, well, if a graph has a corner, it's not differentiable there. So I'm going to zoom in. And I'm just going to put this right here on this corner. And I'm going to hit enter. Okay, there's my absolute value. There's my square root. Looking pretty much the same. Okay, I'm going to zoom in a little bit more. Still looking pretty much the same. Zoom in again. Starting to look a little bit different. Okay, I'm going to zoom in again. Definitely looking different right here. Oops, get this up here. If I can zoom in. Okay, absolute value graph, square root graph. Zoom some more. Absolute value graph, square root graph. Let's zoom again. Okay, that square root graph is looking linear right at that corner right now. So notice that no matter what, on the absolute value graph, I keep zooming in, it never straightens out. It always stays like that. Whereas the one on the bottom went ahead and looked just like a line. Okay, perfectly linear when I zoomed in. So I'm going to say that this guy right here has a derivative at 0. It is locally linear. It wasn't very obvious when we first looked at the graph. Whereas this one, it's not locally linear. That means it's not differentiable there. And we're going to come up with some rules like, well, how would you know that if you didn't zoom in on something like that? Okay, so let's what we're going to say is that, or let's make like a little graph here. So I'm going to make, oops, I want blue. Okay, that it looked like that. And the red one looked like that. Okay, so this is when we zoomed in. And we're going to see that this is locally linear. Thus, differentiable. Whereas this top one never becomes locally linear. I didn't give myself much room. So no matter how much we go in, it's never going to become locally linear, so it's never going to be differentiable at that point. Okay? Okay, so how do you prove, though? So that was nice, but we can't always have a graph. And we said, well, graphs are good to look at. They help us understand what's going on, but we can't use them to prove anything. So that's what I want to know now, is how do you prove a function is differentiable at a point? Again, we can say, well, it's locally linear, therefore it's differentiable, but that's not a proof because that's looking at a graph. Okay, so what we have to do is we have to look at the limits as we're coming from the left and as we're coming from the right. So that's not something we were looking for when we did limits before. Okay, so let's just think about what does that mean? Okay, so let's say I'm looking at that absolute value graph. Okay, so that absolute value graph was here, and it went like that. Okay, so we know it looks like this. Okay, so I'm looking at something different. Like, I don't want to know the limit as x approaches 0. I want to know what are the limits doing as I approach 0. Okay, so it sounds kind of weird. Okay, so notice the limit right here. This is just a line. The limit's down 1 over 1. The slope of that line is -1. So the limit coming from the left is -1. The limit coming from the right, this has a +1. So if the limit from the left does not equal the limit from the right, it's not differentiable at that point. Now, I want you to think about something that's locally linear. If it, evened out like this, again, say I'm way zoomed in, well, the limit as I came from this side would equal the limit as I came from that side. Okay, so let's look at what that looks like right there. So we're going to say a function y equals f of x is differentiable at x equals c. So at some point, if and only if. Now, whenever we use if and only if, oops, here I'm using it already. If and only if, that means that it's a proof that goes forwards and backwards. And a lot of times when we're using the words if and only if, we write this, IFF. And the kids always go, you spelled if wrong. This is kind of standard for if and only if. Okay? So we're going to say if and only if the derivative, which is the slope of the tangent line, as x approaches c from the left is equal to some number. And that number is the same as x approaches c from the right. Okay, so this has to be a number. It can't be infinity. So if they both approach infinity, even though maybe they're both approaching positive infinity from the left and the right, it's not going to work. It has to approach a number from both the left and the right. Okay, so let's put in how we would do that problem that I just showed you. So say I said, I want you to show that f of x equals the absolute value of x plus 1 is not differentiable at x equals 0. Oops. I should have gone up one right there. Okay, well, you'll get the general idea. Okay, so I'm going to say f prime of x as x approaches 0 from the left is equal to -1. F prime of x as x approaches 0 from the right is +1. Or I could just write 1. Since the limits aren't the same, the function is not differentiable. So remember that there's always got to be a conclusion. Okay, now one thing that you have to be really careful about, because this does get a little bit confusing. Again, it's one of those things your brain has to sit on. Okay, the function is still continuous at x equals 0. It's just not differentiable. And the reason is because the limit of the function as x approaches 0 from the left equals 1. Remember, this should be up at 1 right here. That should be 0. And the limit as x approaches 0 from the right of f of x is equal to 1. So that can be a little bit confusing, so watch out for that. Okay?